So have you ever seen this? Press any key to continue. Most of you might be developers, or you might be so young. Okay, so some of the old developers might have seen it. And the point is actually in 1980s, a lot of the tech support questions, most of the dominating companies then were like Apple, Compaq, and this Windows systems. So they had this question from tech support asking for where is any key. So that it was also documented in Apple documentation clearly that don't use the word any key at all. Okay, and even Compaq said that okay, whenever you see any key, it means that return key. So use return previously. So they said okay. So what is the purpose I'm saying it? Because we hear stories in conferences, right? So this is the right place to hear these kinds of stories. So about me, as he has described, I have nearly 10 years of development experience, and then I'm right now working for an awesome company called ThoughtWorks. Most of you may know it. Big technology, I'm like a kind of very big fan of big data technologies. I had 2 startups before this, and prior to that I worked with really good companies. And I'm like the organizer of one of the biggest meetups in Hyderabad called Hyderabad Scalability Meetup. We are really good. We have done like nearly 25 meetups within a span of 6 months, all in big data technologies. So the agenda would be like we try to understand what are the problems that led to the development of Kafka, and then we hear a lot of Kafka stuff today. And I'll show you a small application demo, unless it screws up while showing the demo. And my demo application doesn't actually have this 4.4 million writes per second. That's for sure. Because, sorry? I'm not sure it works because it's an...
Yeah, it does work, but you just have to make some settings. It will be more easier for you to go through this.
Yeah, sure.
Yeah. Just ask for something.
Oh, it's the any key problem, yeah. So shift and then I don't know what that key is.
So I don't want to waste your time.
Yeah, so close it.
Yeah. Sorry.
Yeah, I'm fine. Yeah. So yeah, this is the expectation. So if you see the trends in coding, if you see the 1970s, mostly people are really developing applications which are much into their desktop-based application or whatever the systems that they had. It was all a single kind of application, not much into the integration part. But if you see in 90s, it was most into the web development. So the equivalent amount of coding that was developed and also like equivalent amount of systems that were being integrated into the systems. And 2010s, it is like the amount of coding is less. It's not less in, by the amount of code that is being written, because it should be even more than what 90s had. But if you compare it along with the size of integrations, we are actually trying to integrate a lot of systems together, and then we are trying to code to make this integration work very well. So yeah, that's one primary area where like this kind of problems where Kafka stands out. Okay, let's start with a simple idea. Okay, so I'm like trying to build an analytics application, and which can actually show me kind of current trends, or I can see like if I put a product, if I release a product, I want to understand the sentiment of how the product is being analyzed. So that's my idea. So let us start with Twitter. Okay, so we directly consume the data from the Twitter. So this is how our application may look like right now. So say assume that this is the this is the database, the pink one, and the violet one is Twitter. Okay, so Twitter and our application is quite tied too much that you have this and then it directly process and puts it directly into the DB. And we have some layer which does some little bit of offline processing. So we write this layer after that. Okay, so this is our application. It runs fine. Everything is good. The next one is like let's start including Facebook. Okay, so because Facebook has enough amount of streams. Now this is how I put Facebook in. So I have Twitter at one side, Facebook at other side, and it writes to the database, and then we have some other system which actually pulls the data and puts right a kind of analytics or offline data warehouse kind of thing, the green part. So these are it. Now just imagine if I keep on growing number of input streams and also like number of output streams. So in real use case, a particular stream, like say a log, may be used by different kind of consumers. It's not like it goes and sits at one particular place, and then it's only not the database, right? We actually put it into the database. We also put it into Hadoop systems. We also put it into some other processing system, Storm or something, based on our requirements. So it is always never ending at a particular place. So that's what we are seeing. So once we try doing that, now this is how our application will look like. So the center blue part, right? This is our database, and say the red one is like the Twitter, and this is the Facebook. And this white is twice because it is actually trying to directly write some offline or like some unnecessary or big data or logs into directly into the offline solutions. And some other part of Twitter, which is like these logs or security other things, it is putting directly into some other system. So this is how it gets built. So most of you might have faced into by ending up. So yeah, you can see, right, all these layers are like literally meaningful. So the top one will be like kind of UI layer. We track the UI activity and then push it through some of the layers into the DB. So from UI activity, we also put it into logs. We also put it into database, and it all gets crumpled too much and it becomes something like this. So what is the problem here? We can see two main problems, right? One is like everything is quite tightly coupled, and so I want to put something in, like I want to bring a new input stream, I have to touch a lot of other code. The worst part is like if I want to pull something out, say one of the social network is like not so much worth for me to maintain, so I want to pull it out. I can't pull it out so easily because it is like again integrated with a lot of other systems, and I have to touch those parts well. So that's so it definitely becomes a very big maintenance nightmare. So this is the Kafka story. What made LinkedIn build Kafka? So if you actually go up to what story I've started with our application idea, this is how in 2009 LinkedIn systems looked like. So they had what are the main sources of streams were like they track a lot of user activities. So these user activities were put in, and they had a lot of logs and all these kind of security kind of analytic logs. So they try to pull out a lot of things from different streams and put it into different places. For example, and one of the major and highly performing thing was the Oracle database, but because whenever you put a lot of things in and then ask for it, it is coming well. But the integration part was like quite tough. But they had a little bit bigger challenge. The bigger challenge was that at some point in time, when they tried to actually validate the data, they had two different sources, and two different sources had different types of data. So the same data was like kind of, there was a discrepancy. And then they thought, okay, there may be some problems, so let us check the third data source. When they check the third data source, it has completely different data. And that's when they realize, okay, if we are like trying to do this, all our analytics are going to be wrong, and this is the right time to build something else. And that's when actually Kafka came in. So they started with an idea of something like this. So they all thought about the response times basically. So they said, okay, so whatever is like 0 to 100 milliseconds, which is like really fast, the basic web response, I'll put it into the DB things. So all of those streams will go into Kafka. From there it will all sit in the DB. And then little bit of latency, like 100 milliseconds or I'll do some aggregation operations. So I'll put in those kind of streaming processors. And then from all those go to Kafka, and then actually they'll be processed through streaming process and then come back to Kafka. So people can again consume from there. So if there is like the data warehouse kind of offload processing, they actually move it to Hadoop, and then it processes and then puts the data back there. So you want to process it, you get like latency of more than 1 hour or something like that. So this is like offline data which is greater than an hour. So when they did it, this is what it looked like finally. So this is like completely stream centric thing. So this is the Kafka layer. So whatever the apps were writing, a lot of them were writing to different parts of it even then. But the stream was like it was like completely stream centric. So whatever the different data sources or like where are the producers and consumers were all unified into a single system, and all were talking to a single interface. So that was like the Kafka layer. And if you see, this is how it looks like. So when you build something like this, the base pink one is like something like the Kafka layer. So all of them talk to Kafka layer, and there are like multiple types of producers and consumers which can actually fit in at any different places. For example, this can be removed, or like this can be put in. So when I show it in Lego, it seems easy, but it also seems very easy when you actually do it, because you put a separate layer just to talk to it. It is a consumer, or like it is just a producer. So that's it. The best part is like it also gets distributed. So you can actually do something like this, and then each of them has individual producers and consumers. The advantage is also that you can get a good amount of parallelism. So this is one thing. Sorry. Yeah, so that is like stream-centric design. So when you have a common stream, which where all producers talk and all consumers talk, so based on our requirements, we can actually say, okay, put it into different topics. So I'll come to it a little bit in detail. It's a common thing. Exactly, it is a synchronous queue. It is a synchronous queue. So synchronous, again, it comes with a single little bit of disclaimer. I'll tell about it. So after talking all this, what is Kafka, right? So Kafka can be defined as a publisher subscriber kind of solution, messaging solution, and the next one is like it can be also analogous with the journaling or write ahead logs. So how many of you know about write ahead logs in database? Yeah, quite few of you. So write ahead logs is something like, okay, whenever you write something to the database, it actually writes to write ahead log and then actually does the work. So that whenever anything goes wrong, it actually can replay it from the write ahead log. So it is a continuous sequence of writing. So on high level, this is the simplest definition that I could put it. So producers produce and then consumers consume, but all of them is done in a very large scale. Large is like that big data scale. Distributed, you can be distributed because we get it is like distributed in the sense of horizontal distribution, not like this kind of, and reliable. So when you put something, you ask for it, it is like it's like the true value. It doesn't break anything. And all of this is designed to be in real time. So that's how the whole definition of Kafka falls in. So a little bit of timeline. So it was originally developed at LinkedIn. We saw the story, and then 2011 they actually made it an open source project. 2012 it came out as a Apache project, mostly basically written in Scala, most of the things. And the latest stable version is 0.8.2. So whenever we try to choose any technologies, right, they're like too much technology overload. So we, at least like most of us will try to answer why should we choose it. So there are like a lot of other queuing solutions, right? So whatever I described it, the central streaming solution, there is a lot of other queuing solutions. Say why should somebody choose Kafka? For example, there is ActiveMQ or like RabbitMQ, which is also quite stable, right? That would have solved their streaming problem. So we should actually understand why Kafka. For that, so there are like few characteristics of Kafka which is very good. So it is really fast. So at the order of 1 for reads or writes. And you get a really high throughput. It's 4.4 million writes per second. That's like the LinkedIn with 350 brokers, 350 instances, brokers is instance. And it's scalable. So they have actually horizontally scaled 350 commodity machines. And it is durable. So you know, a lot of queues are not durable. So this also provides you durability. It's distributed, so that's why it's like scalable. And it's replicable. So whenever you want to build any distributed system, you're always very careful about the fault tolerance. So you don't want to take any risk. So still I didn't answer exactly why Kafka, right? So for all the solutions, of all the highly distributed messaging solutions, Kafka definitely stands out. So whatever I have shown. So there are other comparative solutions. One of them is Amazon Kinesis. So they are like in the really same kind of stage. And one more thing is like Apache Flume, but Flume is like for a particular set of use cases. And consumers, so one more thing that we see in Kafka, which is of highest advantage, is all of them, the consumer, when you ask for any message or when you produce any message, all of them are stored in order. So all the other queuing solutions which also store them in order, but when you ask for it, they don't come in order. So they don't take the responsibility of giving you the answers in order. So what happens when you have an user activity and you're actually putting them into the stream? If it is not ordered, this will look something like this. You have an Facebook, so you want to understand Facebook usage, and then you are seeing the activity. The user actually posts something, and then there are likes that are happening, and then he does the login because it all got disturbed. So you actually don't get the real data of the user activity. How many of you know the term mechanical sympathy? Nice. So it is an awesome word. So mechanical sympathy is adopted from actual F1 racing. So there was a guy who is called fastest Scott or something. So this guy used to be always faster than other guys for the same car. So it's a kind of 5 minutes kind of difference. But he was faster even in kind of slippery kind of roads. So when people ask him why, so what made him completely different, he said that there are like, whenever humans are like, so cars are always fast, right? But each part has its own limitation. The hardware has its own limitation. And it's all about you understanding the parts which are like in, where you can actually tackle the limitations very well. And that's how you can be fast. The same was adopted by a guy called Martin. So this guy actually said that, his name is Martin Thompson. And what he said is like software, so when you're writing any software, you should be very closely understanding the hardware part. So when you actually understand that hardware part very well, that's when actually you are actually writing good code. So what Kafka does is like, so they understood the disk part very well. So instead of understanding why it is limited, we can understand why it is better or when it is better. So when is disk better? Disk is far better, or it is sometimes a little bit faster than RAMs when you do sequential reads and sequential writes. So OS has enough advance that you can ask for it for read ahead. So when you ask for, okay, give me 100 MBs of data from this particular location, it goes, fetches 100 MB, it also gets appends another 50 MB, and understanding that, okay, you are going to read it, you're definitely going to ask for it, and then returns you back. That's called read ahead. So that when you ask for something, it actually gives you the whole, like, so next one will not be a disk seek. Disk seek is like literally slow. So that's one thing. The next, the next one is like write behind. So write behind is like, okay, when you are actually writing the file, we talked about reading, right? When you actually write to something to a hard disk, so OS has done something like this. So you actually keep on appending it, and then it does a batch push into the DB. So if you can tap into that, and most of the reads and writes are contiguous. So when you write it, you write at the end. When you read it, you read it from a particular location. So that's why our limitation on disks is quite limited. So what is the next slowest thing? So the next slowest part or the limiting part is the network, right? So network, you have a limited bandwidth, and you can't like, streams are like very big. So sometimes it can, you don't know what happens to the stream, right? When you grow out of it. So that's what they are doing. So they give you an option of doing batching. So first thing is like you can batch things together and then send it together. The next one is like compressing. So you can compress and then send it together. So that's one thing. There's one more beautiful thing that it does. Before coming to that, there's something called page cache. So instead of using the RAM, when you actually write to a page cache, that is actually very better compared to actually using the RAM. Because when you are actually writing it to page cache, it's almost like you are not duplicating the OS caching part. So it is like you tell to the OS that, okay, keep this data there, and it automatically takes care of the caching part. So that's how it is designed. And next one is like, how many of you know that send file command in Linux, or like zero copy? Okay, nice. I'll explain it. So zero copy is something like this. So whenever you want to, so when consumers are asking for data, right? So producers produce, it has been put. We saw like how it is optimized. But when consumers are asking for it, we still are talking about the limitation about the network I/O. So how we can make it better. So this is about two things. One is like how does it saves the local copy. So whenever you ask for something, this is what happens. From the disk, it comes into the kernel's read buffer. And from kernel's read buffer, it comes to the user's buffer or application buffer. And from there, it actually transfers it to the network buffer, and from there it moves to the NIC buffer. Once it is in NIC buffer, it will actually flush out. So that's how the actual transfer of any message happens. So you ask for something, so each one of these happen. So if you ask for 1 million messages, so it is like 4 million copies, because 4 times copying is happening. So what happened is like these guys saw this pattern, and then actually they called, so it is called transfer to in Java, so somebody has written it as transfer to. In Linux, it is like send file. So it actually tries to pull the data directly from the kernel space and then directly pushes into the NIC buffer. So that's one simple call. Having said this, why are not all the other systems using this? Right? Because everybody can use this, right? It is very simple. So this is by design, because when they designed it, it's all about how do you serialize or deserialize things. So how do you store things with you? So in Kafka, when you actually give some data to it, it will actually say, okay, I'm not too much worry about your serialization or deserialization. So I'll just take the data, I'll understand how much size it is, and then I'll actually put a simple message counter saying that, okay, this is offset of 0, and then the next 8 MB of data is going to be, so 0 is the offset, and then after that it will say, I'm saying it at high level, there's still more deeper levels, but so at 0, after 0 the next 4 bytes will say, okay, what is the size of data that I need to fetch? So when you ask for a message, it will go and read that buffer and then just reads that size stream and then gives it to you as a byte array. It will not give it to you as an processed element. And that's why this thing could happen. Otherwise what will happen, it will come here. From here the actual processing or they do the deserialization from their format into the user's format and then actually they send it. That's why it's a little bit slower in other systems. So Kafka at LinkedIn, right? So this is the data as of November 2014. So they have 350 commodity servers, regular normal servers, and these are like highlight numbers. So they have 278 billion messages per day, and the write speed is like 4.4 million writes per second. That's like really good. There is a lot of questions in understanding. Should I use Kafka and how is it different from Storm or Hadoop or Spark, right? So that's the thing. So to put a simple analogy, so this is how it is. So in Linux, if you understand grep, so when you grep, you get a good amount of data, right? So that is like this stream that you are getting in. And this goes through a broker, the pipe, right? That is our Kafka. So this grep, processing of the grep command is Kafka. It is like really big amount of data, big chunk. And from there, when you actually do set, it is actually processing the data. So that processing is sits in one of these things. So whatever you want, you can process it. By the way, you can actually, instead of using any one of these, you can also use the regular actual consumer from Kafka itself. So you have consumers can itself process it. But these are like quite better than these things. So consumers are mostly written in a way to actually do parallel reads. So you should, so yeah, this is the whole idea. And then yeah, so when you have Kafka, you have like this kind of 100K or 500K reads per second into the processing engine. That's like you are using Samza, and then from there you actually put at a small write rate into the actual DB. Yeah, sure. Correct. Right. Right. So instead of you processing it directly, what I'm saying is because you have consumer, you can write the logic there directly to process. But it is putting load on consumers. So you actually give it to Spark or Storm. Right. It is not like top of Spark. It is so from consumer the input goes into Spark. So that's how it is. Because you have parallel reads, right? So there are like it is distributed. Correct. So it's how you design it, yeah. But if your processing is not too much, you can actually say, okay, from consumer itself, put it to something. Yeah. So it all depends on your application requirements. But if you have really big processing, you have to actually move from there to some of this Storm or something. So I'll go through this very fast because when I use some terms, it may be quite overwhelming for you. So any data that we write, so what is a message, right? I keep on saying message, producers produce message, consumer consume message. Message is just something the data. So you have an object or the tweet or like the Facebook post, this is all the data. That's what we call it as message. So producers publish these messages, and messages are stored in different topics. For example, logs can be put into one topic, security logs can be put into some other topic, user activity can be put into one topic. So these are all different topics. And each Kafka server, right, one instance or one process of Kafka server is called a broker. So broker is the regular terminology that we use. And these topics, right, they can be broken into chunks. So for a particular topic, you can say, okay, put it into 3 chunks because I have 3 brokers, put it into 3 brokers. and just replicate it. So put one here or like two here for fault tolerance. So that's the partitioning. And consumer consume from these brokers. So if you have only one broker and then one, it will just pull it, or it will parallelly pull based on your needs. And this is how it is, right? So where Zookeeper comes in, whenever you have cluster coordination, because Kafka runs as a cluster, and Kafka, even if it needs to run at a single instance, it definitely needs Zookeeper. It's like quite closely integrated. And yeah, producer, they send it through TCP and then pull through, consumers pull through TCP, and it is all distributed through the brokers. So, for example, you may have some topic which is like, there are different ways in which we can see this. One is like, how do you, so you have too many number of writes for a particular topic. For example, user activity, right? It is very, very overwhelming. So then, for example, you have one machine. So one topic means it is only one machine, right? You are not partitioning it. So the stream becomes too much big to write. So when you split it out, there are like, it can split out the writes and then it can actually put it there. But more than that, it is from the consumer part. So when it is from one topic, when I'm saying I can give you parallelism in consuming the data, so you cannot put only one topic and then parallelly read from different consumers, right? So you can get, you may be reading the same thing. So you split it into 3 chunks or 4 chunks, and then four consumers can actually pull the data. So you get 1/4 of the time of pulling the data. So that's why partitioning. So any big data, we always talk about partitioning and replication. So partitioning is for scaling. So when you want to, so separate topics you cannot tick. So for different activities you can create separate topics. But how do you say that for a particular topic, right? Topic is a kind of table or something you can understand, and you are actually particular column, and then you are actually splitting the column, so that if you cannot actually create multiple columns, right, for a same data. So you can visualize it in that way. The next one is like, yeah, topics actually, they keep on coming in. One thing very, very different in Kafka is, so in all the other queuing systems, it's something like this. So when you actually write a message, if there are like n number of consumers, for example 5 consumers, once all the 5 consumers consume it, that's it, the data is gone. So that's how it is designed. But here, it is, so the message always stays. It is removed only based on these conditions. So you can say that, okay, after these many, it is per topic level. So you can say, okay, after 1,000 messages, just keep it. It is like, it becomes kind of circular queue. So only 1,000 topics will stay there. Or like you can say by time interval. So you can say, okay, after 1 year, I don't need this data. So flush it after 1 year. And you can also say the size. So you are limited on size. You say till 500 GB of this topic is fine, and then actually clear it off. So that's something we can define it. The next one is like partitioning. So you can actually, so the topic, right, I said you'll actually keep it into multiple things. One is like each individual partition is sequential. So when you consume, right, when I said the consumer guarantees the order of in which you can consume, it is per partition level. It's not like overall partition, because it's not possible. And each message is given an unique ID, so it's something like this. 0 you have this, and then 1, 2 or something like that. So you understood how I stored the data, I told you, right? And then it serves horizontal scaling, because when you are doing it, sorry. Yeah. Right. So, right, that's what so as I said, it is per partition level. So it is not like, if you want to pull the data, which is like sequential, there are 2 ways in which you can do it. One is, you have only one partition. There is no partition at all, so it's on a single topic. But you cannot achieve parallelism. But the other way is, when you store the data, you can actually put a timestamp there. And when you are consuming it, right, once you consume it while processing, you can actually say, okay, order it by that particular field, and then actually, you are deserializing it anyway, right? Put a timestamp while you are putting it, and then actually do it. But that becomes an application overhead.
Assuming that there won't be much delay between non-sequential data, and how long will it keep for ordering, for sorting?
Right. So, I didn't get the question. So,
I mean, there are different chunks, right? There's partition,
Right, right.
So when you are consuming it, you got older message first.
You will not get older message first. So when you are consuming it, it will be like, so the way you wrote it, right, it will be split out based on the partition logic that you write. So you will say, okay, by user ID partition it. So all the user data will be, so for example, if you partition it by user ID, all the per user's activity will be continuous. It's not that, okay, I log in first, login will be first. I post to it first, it will be first. So it doesn't break the order. That's the guarantee it does. So if it doesn't, but if you are doing a user activity and you partition it by something else, then actually the order is lost. So it is like so you can design your application in such a way that when you actually pull it parallelly, it doesn't affect your application. And you can write this default, or so the default partitioning happens, it is like random based, or like you can write your own custom partitioner. So as I said, right, based on your application needs. So basically it works as a traditional model where like producers push and then consumers pull. So all the other ways are like, all the other ways make the servers very heavy because it needs to understand who are the consumers and it needs to push it individually to those consumers. So it is like push versus model versus just producers push and then consumers pull. There are a lot of models in producer consumers, but this is like quite scalable one. There are like reasons or arguments. You can see Kafka documentation. So when we are pushing it, as I said, for better performance, you can actually choose to batch it. So it is like you have to take a question between the durability versus the availability. So when you say that I want, so this is a very important thing, right? Then you say that you need an acknowledgement. So you can define it, okay, just put it to the leader and then come back, or just put it to the leader and this replicas and also come back. It depends on your sensitivity of the topic. So that's one thing. The next one is, if you are not worried too much, so say that is like some debug thing or like some basic logs, you are not too much worried about it, you can say write it in batches. So what it does when producer produces, it keeps it as a batch of 5,000 or 10,000 things and then pushes it at once. So it is like asynchronous push. So you can say 60K messages or 10 millisecond, keep on pushing it. By time or like number of messages you can keep on pushing. And sequential writes are guaranteed, so writes also are guaranteed per partition. So when you send it, it is all. So all the other systems also, writes are like quite guaranteed. So it is by order. And yeah, load balancing, as I said, right? When you can write a partitioner to say how do you want to define the load. It is basically on your application need. If there is nothing too much to worry about, you can give a random partitioner so that it will actually randomly put it. So that's how it is. Next is consumers pull. So when we say consumers, right, the group of consumers which pull, or like there may be different consumers for different topics, right? How does it identify different people? So you can create different groups of consumers, and then you can say this consumer group, four of these and 3 of these, can pull it from the same topic. When this is pulling, how does it understand that, okay, this guy is pulling, this guy has pulled till 100 messages and I need to give the remaining ones. It is like by consumer group ID. So each one has a consumer group ID, and then it's the consumer's responsibility to take care of the messaging ID. So it understands, okay, I have consumed till 100 messages or something like that, and then it keeps an account. What it does, regularly it goes and keeps moving it into Zookeeper. So you can define the interval at which you want to tell it to the Zookeeper to actually coordinate. So consumer group IDs are stored there, and then next time I failed on, this consumer group failed on, the next time it comes up, it doesn't start from the beginning, but it talks to the Zookeeper to see, okay, this guy has already consumed 500 messages, let me give it from 501. So that's how it does. But this was still last release, and recently they had done some changes where like they're also putting it as a separate topic, the consumer consumption message ID, right? So that group ID and then the message till it has consumed, they're putting it as a separate topic. And one good part, or like not other machines are doing, other systems are doing it. So you can prevent the offset. For example, if you are running a Hadoop cluster, you're consuming the messages, and you found that, okay, this map reduce, I have a bug, I want to rerun it. So other machine, so the regular kind of producer consumer model, you lose all the things that you got. Either you store it in HDFS or like you have lost it. So here you can actually rewind the offset. You will say, okay, just make it to 0, consume it from the beginning. So it's under your control. And guaranteed order per partition, as I already said. So more partition enables more parallel reads. So if you have, so it all depends on how many, your usage scenario. And most important, if for a particular topic, if you have 5 partitions, you cannot define more than 5 consumers. It only gives one consumer, one topic, one partition. If you define 10 consumers, you cannot see the parallelism. So 5 consumers are literally waiting, they don't do anything. So it's not per broker, it's per partition level. One broker can have, so that's what I'm just showing. so say here we have 4 brokers. And then we have one topic, okay, we'll take a simple topic. And I'm saying it to divide into 2 chunks, that's it, 2 partitions. And I'm saying replication factor of 3. So what it does, I think it should be clear, okay. Anyways, so there are like broker 1, 2, 3 and 4. So for part 1, it puts it into 3 replicas. And in the next one, it puts 3 replicas. So it's always 3 replicas there. Now what happens? Anything you define, there is a leader and then 2 followers. Sorry. So topic 1, so if you understand the first half, right? The first half of the partition is in 3. The second half of the partition is in 3. So replication factor is 3, right? So that's why it is 3. So this machine goes off, it's always there. So this machine goes off, it's always there, something like that. But it is always designed in a way, we always have n-1 kind of, so if you define replication factor of 3, it can handle till one machine is alive. So if this machine goes off, it automatically puts it back here. So it will automatically do that. So automatically failover is already designed. So there is always one leader. So that leader is only responsible for writes and also for consumption. So if you ask for, just a minute. Yeah, no, it's only for, the leader is for writes. So when you actually write anything, it will actually say, okay, write it only to the reader and followers will keep following up. Okay. So this we call it as in-sync replicas. So in-sync replicas we can define a particular factor. For example, we can say, my replication factor is 3, right? I can say till 2, if in-sync replica is fine for 5 seconds, assume that my system is safe. If in-sync replica goes beyond, like say, it becomes only 1, like only 1 is alive, I think then actually it is like, all these are like kind of administrative things. So you can define how safe your data can be. So if this is understood, I think most of the part of Kafka is understood. So because if you design this very well like this, you can design beautiful producers and you can have awesome consumers because all of them is parallelized. So next one is like message delivery guarantees. So what are the guarantees that we have? One is like, so you read the data and then you save the, so you read the data, you say, okay, I read the 5 messages and then I say 5, I said, okay, I saved 5 and then I actually process it. And then the processing fails. Now again read the data. I don't have it because I already said that I have read till 5. So that is like at most once. At least one is something like this. So you read the data and then you process it. Once the processing in 5, then you go and write it. But what happens? If you read, process and then you don't, while saving, the saving fails, you are again reading the same data. Unless it is idempotent, it is not so good. Exactly once is like kind of ideal situation, right? All of us want. So with Kafka, at least once delivery is by default. So you'll always have the guarantee that you'll at least read once. And at most once, all this you can design by design. So you can, there are ways in which you can design it. So at most once is like by configuration. But if you want exactly once, it is something like this. So I'll tell you very fast. So for example, Hadoop is consuming it. You also say Hadoop itself, HDFS itself to maintain the message position. So both are at the same place, it will not fail. If it process and consume, then both are like, it's kind of two-phase commit at that level, at the consumer level. So that you have to implement by yourself. A lot of people have implemented, so if you want to search for it, you'll actually get it. Okay. So you already have consumed till 500 messages, but next time you have again started from the basic and you have consumed till 450. So you want only the 50 to be processed. So that 50, to understand that, you have to do it from your application side. Yeah, because either you have to have that exact guarantee of exactly once. If you don't do it, then you will have that duplication. So you have to handle it from your side. So yeah, you want to handle this exactly once scenario. You cannot merge them. Yeah, it is like on your application actually. So you can completely create a new set of consumer group and then pull the data. If you have some reference to that data, you can actually compare this and then see till what you have consumed. So these are all the regular use cases. So one thing is the messaging part. So it is equivalently comparable with ActiveMQ or this thing, but it's more distributed. So as I said, there are like quite good amount of advantages. The next one is like web activity tracking. LinkedIn is using it very heavily for web activity tracking. So web activity tracking sends you a lot of these events. So you do a mouse here, mouse over, click, everything is being tracked. So per user, if you have 1 billion users, it's like per user, per page into that multiplication. So then you get a lot of data. So that's one thing where you can use. The next one is like operational monitoring. So you have multiple machines, and we normally do operational monitoring through logs or something, right? So from the logs you can actually aggregate these logs. And it's also like log aggregation is also same thing. So you have multiple logs from last say 10 years, and then you have accumulated it across different machines. Now you want to pull it to a single place, or like you start now and then you are having multiple places which are talking to logs. Instead of logging it there, you can have a centralized place to log this. So that's one thing. Logs are always good because normal logs also it keeps on appending it, so it's really fast. Next one is like stream processing. So as I said, you actually pull the data, and then while consuming, you give it to Spark or Storm directly. So that's how it is. And event sourcing is like a timeline of an. So how many of you have heard of event sourcing? So event sourcing is something like you create a timeline of an object state. For example, you can. So if objects keep on changing from one state to other, you can go and say, okay, what is the state at? So what is it truth proof for that particular time? So that's what is event sourcing. It's a little bit deeper, but you can go and search for it. Next one is like commit log. So the journals or like the commit log, whatever I said. So there is something called Apache Zookeeper. It also like sits in the same kind of layer. You can use it as a reliable commit log. So yeah, that's one more thing that I have. So I have done a small application. So this is how it is. So what I'm trying to do is, so I have, so what I have done is like, I'll put it in Git if you want to use. Okay, are you able to see this? Okay. So it is like, yeah. I'll just put this off. So these are all the producer properties, and as I said, right, for each producer you can say, okay, this is the producer type is async, or you can batch and all those things. You can do it. And I have put everything as a property file, and this producer actually takes it, and actually it reads through Kafka stream. It reads through Twitter and then puts it. So, okay, this is a very big code. Like you can search for the GitHub link, and then actually you'll get a lot of this code. Okay. And I'm just taking the property file directly and then I wrote a simple producer to actually consume the Twitter stream. What it does is, every time it gets a Twitter tweet or whatever it is, based on the type of event, it has a listener. So on status, I'm only capturing the status events. So on status, I'm actually trying to put it into the stream. So this is the producer part. So producer is actually consuming the stream of Twitter data. And then I have the consumer, okay. So consumer properties I have defined the same way. For consumer, you don't need to specify. You can see, right? Yeah. Consumer, you need not go and specify all the broker IDs or Kafka IDs, because the common coordinator is Zookeeper. So it can ask from Zookeeper from where I can start consuming it. And you can say, this was what I was saying. So what is the time in which you want to give the limit for consumption. So here I have 3 consumer threads because I have 3 brokers. So the architecture is something like this. I have 3 instances of Kafka running in different ports, and that's like this. So these are the 3 different 9092, 9394, and definitely needs Zookeeper. So I start Zookeeper, and I start 3 instances of Kafka, and I define the properties of consumer and producer. And I have this application property. This is for the Spring Boot. Okay, I use Gradle and Spring Boot, and this is something like this. So this is what it does basically. So it's simply so I didn't use any database. I'm just using an in-memory map. So it just gives me a count of how many messages are consumed by per consumer thread. I'm just writing a simple application. So this is how it is. I just call the Twitter stream API, and then I just start it as a separate thread. This is a separate thread. So the producer keeps on consuming the data. The next one is like the Spring application boot. So it starts the embedded Tomcat. So it starts it from there. And then I have consumer, and then I say start consumer. So as I said, in consumer I have written number of threads it wants to read, right? So in consumer I want to show only one part. So when you consume, so this is how it is. When you consume something, right? This looks weird on the first time, but yeah, once you get used to it, it's okay. So you can say, so this is how it is. So when you actually consume the data, right? So I'm saying these are the number of streams that I get, and based on the streams, I actually consume the data, right? Now while consuming, you only get a byte array. That's what I am going to say. So you actually only get bytes. I said, right, that message thing. You have that message ID. Next it will say this much amount of byte. You only get that bytes kind of thing. So from the byte, you have to actually decode it. So I'm using a decoder, and then that decoder gets my action, converts it into my object. So I'm using some kind of JSON decoder, and so I'll just get it. Right. Yeah, now I have done something like that. So I used AngularJS in the front end. So AngularJS, I'm actually, so if you actually see it, right, this is simple AngularJS, and it keeps on polling. Okay, so if you see this code, it keeps on polling. So it's an actual REST call. Okay, Kafka/data. So I have a controller. Just since it is single thing, I just kept it here itself. And see, it is a REST actually. It's a REST controller. So that it keeps on calling the REST controller at the defined specific polled amount of time, and then gives me the consumer count. So let us see if it is parallelly reading it or not. Okay. Okay, so it started. Okay. So here, so you can see it, right? So is a total amount of tweets. It is like per consumer how much it is consuming. So it's parallel consuming it. So it keeps on consuming till the producer. So till that limit is done. After that, the producer it has to wait for the producer. So I actually pulled some data and then kept. So I have run it for some time so that it already has some data. Now it keeps on pulling, and one consumer will it keeps on consuming after some time. So that's how it is. So yeah, I'm almost done. So I think I'm on time. Yeah, you can follow me here. So I have this presentation actually published at openscalability.com. So you can actually go there, and this is actually I'm directly presenting from there. So you can actually go and I'll actually update with the GitHub link. I didn't commit it because in ThoughtWorks we actually mostly believe in test-driven development. I didn't follow that, so I said, okay, I'll not commit it. But anyways, I'll commit it because this is just a demo kind of thing, and